Welcome to Chapter 4.6, Electronegativity and Bond Polarity. Electronegativity is possibly one of my favorite words. It's because it comes up so much, and as you hopefully move on in chemistry, some of you may or may not, it is very, very useful in determining bonding patterns and a lot with organic chemistry. And so, of course, I like that since I am an organic chemist. So you will want to expect this to be on the test for sure, because it's one of my favorite concepts. Okay, what is electronegativity? Sounds like a long word, but basically it is the tendency for an atom to attract electrons to itself in a shared bond. So in a covalent bond that we've shown, so we've hopefully just watched the video on covalent compounds. So if we have just something simple here, so if we have H2, okay, they're sharing these electrons in a covalent bond, and it's the tendency for one atom to attract the electrons, so to pull harder. So in my classroom, I like to show this, but we kind of play tug of war. So I'll talk more about this, but basically is one atom pulling harder on those electrons, and is the bond uneven? So is the electron distribution uneven? Okay, electronegativity increases from left to right going across a period. Okay, and so if you get out your periodic table, you're going to look at, as you move left across the periodic table, it's going to increase. Okay, and as you move down, it's going to decrease. Okay, it's very high for nonmetals. So fluorine is the highest. So one way to remember this trend is basically if you move away to the left or you move down from fluorine, you're becoming less electronegative. Okay, and it's very low for metals because metals, they want to lose electrons, right? So it makes sense. They don't want to hold on to them. Electronegativity is the attraction, or to pull tightly on those electrons. Okay, so our nonmetals do this because they want to gain electrons. Okay, so here's a chart. You will not have to memorize these values. Okay, it'll be given to you if you need it in that way. You basically just need to know the trend. Okay, but if we look here, the electronegativity of fluorine is 4. It is the highest. Okay, so as we move across here, electronegativity increases. Okay, so the ability to pull on electrons and attract electrons towards itself. Okay, so fluorine does this the best. As we move down, it also decreases. So if you move away or you move down from fluorine, you're decreasing electronegativity. Okay, so what does this tell us with respect to bonds? Okay, and with bonds. So we've looked at ionic bonds between nonmetals and between metals and nonmetals. Okay, and we've also talked about covalent bonds. Okay, we've talked about how covalent bonds share electrons. Okay, well, within the kind of umbrella effect here, we have covalent bonds, but we have two types of covalent bonds. We have nonpolar and we have polar. Okay. Another key thing here, to determine if it's nonpolar or polar, polarity is based on electronegativity. So EN is my abbreviation for electronegativity. Okay, if we say that a bond is nonpolar, this means that the electrons are shared equally between two atoms. Okay, so if we look here at two hydrogens that are bonded to each other, okay, and if we look at the difference in their electronegativity, so if you go back to your chart, hydrogen has electronegativity of 2.1, okay, but we have two hydrogens, so 2.1 minus 2.1 equals 0. Okay, so we would call this nonpolar. Okay, that means that there is no difference, no or small, we'll talk about how small, difference, that's my little change right there, that means difference, in electronegativity. Okay. If we have a covalent polar bond, electrons are going to be shared unequally. So basically, one atom is going to be tugging harder on the electrons. So if we think about something like HCl, okay? So if we look at the electronegativity value, hydrogen's 2.1, Cl is 3.0. So 2.1 and 3.0. Okay, so we have a larger difference in electronegativity. Okay, so it's kind of on a scale. So you have, no difference to a very small difference is nonpolar. Okay, but if you have an unequal sharing, okay, so here we would have a difference of 0.9. We call this a polar covalent. Okay, remember it's covalent because these are nonmetals. So we have no difference is a nonpolar covalent in electronegativity. If we have a small difference or intermediate difference, then it is a covalent polar bond. And if we have an ionic bond, then we have a large difference. Okay, but remember ionic is metal and a nonmetal. And this makes sense. If we look back at our periodic table here, if we have Na and Cl, we have a 3 and a 0.9. So we have 3, so let's just say this is Na. So we have 3 and a 0.9. So we have a difference of 2.1. So we have a large difference, which makes it ionic, and have a large electronegativity difference. Another thing that may help you as when you're looking at two atoms and comparing electronegativity, the further away they are from each other, the more electronegative. So this makes sense. If we have a metal, it's way over on the left side of the periodic table. If we have a nonmetal, it's way over here. So they have a large difference in electronegativity. This is what makes them ionic. Okay, if they have no difference, so if they're the same O2 is bonded to itself, it's nonpolar because there's no difference. It's the same. It'd be 3.5 minus 3.5 equals 0 difference in electronegativity. Okay, if we have a moderate difference, so we have a little bit of difference. That was like our example of HCl. Okay, we have two nonmetals. Okay, that's what makes it still covalent. We have two nonmetals, but there is a difference in electronegativity. Okay, so here's showing the equal sharing. So we've already shown this of hydrogen. So there's equal sharing, so we consider it to be nonpolar covalent bond. The equal sharing means that it is nonpolar. And equal sharing refers to the fact that there is a small or 0 difference in electronegativity. For HCl, we saw that we have unequal sharing. So if we were to play tug-of-war with the hydrogen and the Cl, so here's our rope that would be in between, and we played tug-of-war. Okay, electronegativity says that whichever atom's more electronegative, it's going to pull electrons harder to itself. Okay, so basically the chlorine is winning the tug-of-war. It's pulling harder on these electrons. So there's electrons in here, and it's pulling harder, so it's winning the tug-of-war. Okay, so if it pulls electrons harder to itself, then it's going to have a partial, that's what that little symbol is there, it's a partial negative charge, because electrons are negatively charged, so it's pulling negative charge closer to itself, and kind of leaving this hydrogen as a partial positive charge, okay, because it lost. It lost the tug-of-war, because it's less electronegative. Okay, chlorine is more electronegative. So we have a large enough difference in electronegativity to make this bond polar, covalent. Okay, so here's some examples of bonds that are nonpolar covalent bonds. Okay, so we have two of the exact same atom, so that's automatic nonpolar because there's no difference. Okay, and we have a couple of other examples where we only have a small difference in electronegativity, and so we call these nonpolar. Okay, we only have a 0.2 or a 0.3. For polar covalent bonds, still these are nonmetals. Okay, there's unequal sharing. So previously we consider it to be equal sharing with the nonpolar. Okay, for polar, it's unequal sharing, and there's a moderate electronegativity difference. So if we look at all these examples and you were to use your electronegativity chart to compare, you would have a difference of 0.5, 0.5, and 1. And we consider these to be polar because they have a moderate difference in electronegativity. And they are covalent because they're nonmetals. And then an ionic bond is a metal and a nonmetal. And remember, this is a transfer of electrons, whereas our covalent compounds were sharing. Hopefully you've picked up on that previously. But these have a large electronegativity difference of 1.8 or more. Okay, so here would be examples where we've got metal, nonmetal, metal, nonmetal, metal, and a nonmetal. Okay, so these are considered ionic when they have a very large difference in electronegativity. So kind of the cutoff point for each of these is a nonpolar covalent has an electronegativity difference of less than 0.4. A polar covalent bond has a electronegativity difference greater than 0.4 but less than 1.8. An ionic has a electronegativity difference of greater than 1.8. This is kind of the cutoff. I wouldn't try to give you ones that are right on, or hopefully they'll be obvious to you. But 0.4 or less, nonpolar covalent. Greater than 0.4 but less than 1.8 is polar covalent, and ionic is greater than 1.8 electronegativity difference. And once again, polarity is based on electronegativity. Okay, so let's practice. Let's identify as nonpolar covalent, polar covalent, or ionic. Okay, for A, we have K and N. We have a bond between potassium and nitrogen. So if you look on your periodic table, hopefully you see that you have a metal and you have a nonmetal. So we have a metal and a nonmetal. So this must be ionic. Okay. For B, we have two nonmetals. So right away we know that this is covalent, but we don't know if it is, we're trying to determine if it's nonpolar covalent or polar covalent. Okay, so if we look back at our chart here, okay, if we look at nitrogen and oxygen, we have a difference of 0.5. Okay, and we know that a difference of 0.5 means that we have a polar covalent bond. Okay, we have two chlorines, so we have two nonmetals, and they're the same atom bonded to itself, so we automatically know that this is going to be nonpolar. There's zero difference in electronegativity. Okay, HCl, we've actually already done this one, but we've got two nonmetals, and we have a difference of electronegativity. I think it was of 0.9, or it was greater than 0.4, so we know that we have a polar covalent bond. All right, this concludes the video on electronegativity.